In the realm of software development, establishing a baseline serves as a critical milestone, marking a point of stability and agreement from which progress can be measured and managed effectively. A baseline essentially captures a snapshot of the project's current state, encompassing various artifacts such as approved requirements documents, design specifications, source code, and test plans. By freezing these elements at a specific point in time, we create a reference point that facilitates clear communication and coordination among project stakeholders. The primary purpose of establishing a baseline is to mitigate project risks and vulnerabilities by introducing a structured approach to change management. Without baselines, software projects can easily spiral into chaos, with modifications being implemented haphazardly, leading to scope creep, integration issues, and an inability to track progress accurately. Baselines act as checkpoints that allow project managers to assess the impact of proposed changes, ensuring that they align with the overall project goals and constraints. Furthermore, baselines promote accountability and transparency within the development team by clearly defining what constitutes a completed deliverable. At each stage, baselines provide objective criteria for evaluating progress and identifying potential bottlenecks. This transparency fosters a collaborative environment where team members have a shared understanding of the project's status and their individual responsibilities. In conclusion, baselines are an indispensable aspect of successful software development, providing a stable foundation for managing change, mitigating risks, and ensuring that projects stay on track. By establishing clear checkpoints and reference points, baselines empower development teams to deliver high-quality software within budget and time constraints. As technology advances at an unrelenting pace, organizations often find themselves grappling with legacy software systems that struggle to keep up with evolving business needs. These outdated systems, while potentially still functional, may suffer from a myriad of issues such as poor performance, scalability limitations, security vulnerabilities, and a lack of integration with modern technologies. This is where software re-engineering comes into play, offering a lifeline for breathing new life into these aging systems. Software re-engineering is the process of thoroughly analyzing, restructuring, and modernizing existing software applications to enhance their functionality, efficiency, and maintainability. It goes beyond mere code refactoring, involving a comprehensive examination of the system's architecture, design patterns, and underlying technologies. By identifying areas for improvement, re-engineering aims to optimize the system's performance, enhance its security posture, and extend its lifespan. One of the primary drivers behind software re-engineering is the need to adapt to changing business requirements. As organizations evolve, their software systems must keep pace with new demands, such as supporting mobile devices, integrating with cloud-based services, or complying with updated industry regulations. Re-engineering allows businesses to leverage their existing software investments while adding new features and capabilities to meet these evolving needs. Moreover, re-engineering can significantly improve the efficiency and maintainability of legacy systems. Outdated code bases often suffer from code rot, characterized by convoluted logic, poor documentation, and a lack of modularity. Re-engineering addresses these issues by refactoring the code base, improving its structure, and implementing modern programming practices. This results in a more maintainable system that is easier to understand, modify, and enhance in the future. In summary, software re-engineering plays a crucial role in extending the lifespan and value of legacy systems. By modernizing their architecture, enhancing their functionality, and improving their maintainability, re-engineering enables organizations to adapt to changing business needs while maximizing their existing software investments. In the pursuit of delivering high-quality software, it is imperative to understand the distinct yet complementary concepts of verification and validation. While often used interchangeably, these two processes serve different purposes and are essential for ensuring that software meets its intended objectives and user expectations. Verification, often referred to as building the product right, focuses on evaluating the software development process itself. It involves a series of checks and balances throughout the software development lifecycle to ensure that each stage adheres to predefined standards, guidelines, and specifications. Verification activities include code reviews, design inspections, and testing to detect and correct defects early in the development process. Validation, on the other hand, aims to answer the question, are we building the right product? It focuses on evaluating the software product itself to determine whether it meets the user's needs and requirements. Validation activities typically occur later in the software development lifecycle and involve techniques such as user acceptance testing, beta testing, and real-world simulations to gather feedback from end users and stakeholders. The key difference between verification and validation lies in their scope and objectives. Verification aims to ensure that the software is built according to the specified requirements, while validation seeks to confirm that the software fulfills its intended purpose and satisfies user needs. Both processes are essential for achieving software quality, as a system can be verified without being validated, and vice versa. To illustrate, imagine a team developing a mobile banking app. Verification activities would involve reviewing the code for adherence to coding standards, testing individual modules for functionality, and ensuring that the app integrates seamlessly with the bank's back-end systems. Validation, however, would involve testing the app with actual users to assess its usability, security, and overall satisfaction in real-world scenarios. In conclusion, verification and validation are two sides of the same coin when it comes to software quality assurance. While verification focuses on building the product right, validation ensures that we are building the right product. By employing both processes effectively, software development teams can deliver high-quality software that meets both technical specifications and user expectations. In the ever-evolving landscape of software development, computer-aided software engineering tools have emerged as indispensable assets, empowering developers to streamline their workflows, enhance productivity, and deliver high-quality software more efficiently. Case tools encompass a broad spectrum of software applications designed to automate and support various phases of the software development lifecycle, from requirements gathering and design to coding, testing, and maintenance. At their core, case tools aim to automate repetitive tasks, improve collaboration among team members, and enforce best practices throughout the development process. By providing a centralized repository for project artifacts, case tools foster better communication and reduce the risk of errors caused by miscommunication or inconsistent information. Case tools can be broadly categorized based on their functionality and the software development lifecycle phases they support. Some common types of case tools include requirements management tools. These tools facilitate the elicitation, documentation, analysis, and management of software requirements. They provide features for creating use cases, user stories, data flow diagrams, and other artifacts that help capture and communicate user needs effectively. Design tools. Case tools for design assist in creating visual representations of the software system's architecture, components, and interactions. These tools support various modeling techniques such as unified modeling language, entity relationship diagrams, and flowcharts, enabling developers to design robust and maintainable systems. Coding tools. This category encompasses a wide range of tools that support the coding phase, including integrated development environments, code editors, debuggers, and version control systems. These tools streamline the coding process, automate code generation, and facilitate collaboration among developers. Testing tools. Case tools for testing provide automated and manual testing capabilities, enabling developers to identify and rectify defects early in the software development lifecycle. These tools support various testing types, such as unit testing, integration testing, system testing, and performance testing. By leveraging the power of case tools, software development teams can reap numerous benefits, including increased productivity. Automation of repetitive tasks frees up developers to focus on more complex and creative aspects of software development. Improved collaboration, centralized repositories, and communication features foster seamless collaboration among team members, regardless of their physical location. Enhanced software quality enforcement of coding standards, automated testing, and early defect detection contribute to higher quality software. Reduced development costs. Increased efficiency, fewer errors, and faster time to market translate into significant cost savings. In conclusion, case tools have become indispensable assets in modern software development, empowering teams to work smarter, collaborate effectively, and deliver high-quality software that meets user needs. By embracing the capabilities of case tools, organizations can streamline their development processes, reduce costs, and gain a competitive edge in today's rapidly evolving technological landscape. Section 5. The Blueprint of Software. Success. Understanding the Software Requirement Specification, or SRS. In the intricate world of software development, where complexity reigns supreme, the Software Requirement Specification stands as a beacon of clarity, guiding the entire development process from inception to completion. Serving as the blueprint for software projects, the SRS meticulously documents the functional and non-functional requirements of the software system, ensuring that all stakeholders share a common understanding of what is to be built. The SRS acts as a contractual agreement between the development team and the client or stakeholders, outlining the scope of the project, the desired functionalities, and the quality attributes of the software. It serves as the foundation upon which all subsequent development activities are based, from system design and coding to testing and deployment. A comprehensive SRS typically comprises several key components, each playing a crucial role in defining the software system. First, there's the introduction. This section provides an overview of the software system, its purpose, and its intended audience. It sets the context for the document and introduces the key stakeholders involved. Next, the overall description. This section delves into the details of the software system, describing its functionalities, user interfaces, hardware and software constraints, and any external interfaces with other systems. Then we have the specific requirements. This section forms the heart of the SRS, meticulously outlining the functional and non-functional requirements of the software system. Functional requirements describe what the software should do, while non-functional requirements define how well the software should perform its functions. Following that, the constraints. This section outlines any limitations or restrictions that may impact the design or development of the software system, such as budget constraints, regulatory compliance requirements, or technical limitations. Lastly, assumptions and dependencies. This section documents any assumptions made during the requirements gathering process and identifies any external dependencies that may impact the project's success. The importance of a well-defined SRS cannot be overstated. It serves as the single source of truth for all project stakeholders, ensuring that everyone is on the same page and working towards a common goal. A clear and comprehensive SRS reduces misunderstandings by explicitly documenting the requirements, minimizes the risk of misinterpretations or conflicting assumptions among stakeholders. It also facilitates accurate estimation. With a clear understanding of the requirements, the development team can provide more accurate estimates for project timelines and costs, and it improves communication. The SRS serves as a communication tool, facilitating effective communication among developers, testers, project managers, and stakeholders. In conclusion, the Software Requirements Specification is an indispensable artifact in the software development process, providing a blueprint for success by clearly defining the software's functionalities, qualities, and constraints. A well-crafted SRS fosters collaboration, minimizes risks, and paves the way for the development of high-quality software that meets user needs and business objectives. Section 6. Navigating the complexities of the spiral model. Weighing the drawbacks. The spiral model, a risk-driven software development lifecycle approach, has garnered both praise and criticism for its unique approach to managing risk in complex projects. While its iterative nature and emphasis on risk analysis offer distinct advantages, the spiral model also presents certain drawbacks that warrant careful consideration before adopting it as the preferred SDLC methodology. One of the primary drawbacks of the spiral model lies in its complexity. Unlike linear or iterative models, the spiral model's cyclical nature, with its multiple iterations and risk assessment phases, can be challenging to comprehend and manage, particularly for teams unfamiliar with its intricacies. The model's flexibility, while beneficial in adapting to changing requirements, can sometimes lead to scope creep if not managed effectively. Another significant drawback is the potential for cost overruns. The iterative nature of the spiral model, with its emphasis on risk analysis and prototyping, can lead to increased development time and costs, especially if risks are not adequately identified and mitigated early on. The model's reliance on experienced risk assessors and skilled developers further contributes to its cost intensiveness, making it less suitable for projects with limited budgets. Furthermore, the spiral model's heavy reliance on documentation and communication can be perceived as bureaucratic and time-consuming. Each iteration requires thorough documentation of requirements, design decisions, and risk assessments, which can add to the project's overhead, particularly in fast-paced environments where agility is paramount. Moreover, the spiral model's success hinges on the expertise of the development team. Its effective implementation requires experienced risk assessors who can accurately identify and analyze potential risks, as well as skilled developers who can adapt to changing requirements and deliver high-quality code within tight iterations. Finding and retaining such talent can be a challenge, especially for organizations new to the spiral model. In conclusion, while the spiral model offers a robust framework for managing risk in complex software projects, its complexity, potential for cost overruns, reliance on documentation, and need for specialized expertise pose significant drawbacks that must be carefully weighed against its benefits. Organizations considering adopting the spiral model should assess their project's complexity, risk tolerance, budget constraints, and team's expertise before making an informed decision. Section 7. Prototyping and proof of concept, early validation for software success. In the dynamic world of software development, where user expectations and market demands are constantly evolving, it is crucial to validate ideas and concepts early in the development cycle to minimize the risk of building the wrong product. Prototyping and proof of concept emerge as invaluable techniques, allowing development teams to gather feedback, test assumptions, and make informed decisions before investing significant time and resources in full-scale development. Prototyping involves creating a simplified, working model of the software system or a specific feature to demonstrate its functionality and user interface. Prototypes can range from low-fidelity mock-ups created using paper or simple design tools to high-fidelity interactive prototypes that closely resemble the final product. The primary purpose of prototyping is to gather feedback from users and stakeholders, identify usability issues, and refine the design before committing to code. Proof of concept, on the other hand, focuses on demonstrating the feasibility and technical viability of a particular concept or technology. It aims to answer the question, can we build this? Proofs of concept typically involve building a small-scale implementation of a specific feature or integration point to validate its technical feasibility and identify any potential roadblocks. Both prototyping and proof of concept play crucial roles in the early stages of software development, albeit with distinct objectives. Prototyping emphasizes user experience and design validation, while proof of concept focuses on technical feasibility and risk mitigation. The benefits of incorporating prototyping and proof of concept into the development process are manifold. Early feedback and validation. Prototypes and proofs of concept provide a tangible representation of the software concept, allowing stakeholders to provide feedback and validate assumptions early on, reducing the risk of costly rework later. Improved communication and collaboration. Prototypes serve as a common language between developers, designers, and stakeholders, fostering better communication and collaboration during the design and development process. Reduced development costs. By identifying usability issues and technical challenges early on, prototyping and proofs of concept help minimize costly rework and ensure that the final product aligns with user needs and technical feasibility. In conclusion, prototyping and proof of concept are invaluable tools in the software developer's arsenal, enabling early validation, reducing risks, and fostering a user-centered design approach. By incorporating these techniques into the development process, teams can increase the likelihood of delivering successful software products that meet user expectations and market demands. Section 8. The incremental model, delivering value in stages. In the realm of software development, where agility and adaptability are paramount, the incremental model has emerged as a popular approach, allowing teams to deliver value to users in manageable stages, rather than waiting for a single, monolithic release. This iterative methodology emphasizes flexibility, feedback, and continuous improvement, making it particularly well-suited for projects with evolving requirements or those where early and frequent releases are desired. The incremental model divides the software development lifecycle into a series of iterations, each producing a working increment of the software system. Each increment builds upon the previous one, adding new features or functionalities until the complete system is delivered. This iterative approach allows for early and frequent feedback. Users and stakeholders can provide feedback on each increment, allowing the development team to incorporate changes and improvements in subsequent iterations. Reduced risk. By delivering the software in stages, the incremental model reduces the risk of delivering a product that does not meet user needs. Early increments provide valuable insights into user expectations, allowing for course correction throughout the development process. Flexibility and adaptability. The incremental model is highly adaptable to changing requirements. New features or functionalities can be easily incorporated into subsequent increments, allowing the software to evolve with changing business needs. Improved quality control. Each increment undergoes rigorous testing and quality assurance, ensuring that defects are identified and addressed early on. The incremental model offers several advantages over traditional waterfall methodologies, particularly in today's dynamic software development landscape. Faster time to market. Early increments allow users to start benefiting from the software sooner rather than waiting for a single large release. Increased user satisfaction. Frequent releases and continuous feedback loops ensure that the software evolves in alignment with user needs, leading to higher user satisfaction. Better resource utilization. The incremental model allows for better resource utilization as development teams can focus on delivering smaller, manageable increments rather than being overwhelmed by a single large project. In conclusion, the incremental model provides a flexible and iterative approach to software development, emphasizing early feedback, risk mitigation, and continuous improvement. By delivering value in stages, the incremental model enables teams to adapt to changing requirements, deliver software faster, and achieve higher user satisfaction.